Okay, so let's have a look at this first question. A golf ball is hit from a point O on a horizontal ground and moves freely under gravity. Horizontal and vertical components of the initial velocity are 2u and u respectively. The ball hits the horizontal ground at a point whose distance is 80 metres away from O, and A is to show that u must be equal to 14. So let's have a look. So this is number 1A, and as usual we'll do a little sketch. So actually do a little sketch. So horizontal ground, projectile, horizontal component is u, and the vertical, 2u. Yeah, horizontal is 2u, and the vertical component of velocity is just u. Okay. Now the distance that we're going to is going to be 80 meters along here from O to the point where it reaches the ground. Okay. R. I'll call it R. Okay. Now so we're going to first of all consider the horizontal motion. So horizontal motion, and I know the distance 80. I know the initial velocity is 2u, and I also know, of course, that the initial velocity is the same as the final velocity because nothing changes. There's no acceleration in this direction. So for our horizontal motion, we know that the Suvat equation that we need is going to be S equals ut plus a half at squared. But a is 0 because we've got no acceleration. So for the horizontal motion, we're going to have S equals ut, or ux, the x component of velocity, times t. Right. So all we've got to do is plug in our initial velocity, which is 2u, and our distance 80. So therefore 80 equals 2u, initial velocity, times t. And from this we can deduce that therefore the time it takes to travel from O to R must be 80 over 2u, which is equal to 40 over u. Okay, so we don't know what u, so we know what the time is in terms of u, which we've been given, and now we want to consider the vertical motion in order to work out, to get another equation, and we can use it as, so now consider the vertical motion. Which I'm going to use, because I'm going to have acceleration acting downwards. That's the value of g, which is 9.8. We're going to take g to be 9.8 meters per second squared. Sorry. I'm going to use upwards as positive. So upwards as positive. And we need to now consider the vertical motion. Right, now the vertical motion we're interested in is going to be the motion from O to R. So our initial velocity is going to be u. So the velocity in the y direction, uy, is actually equal to u. And of course this velocity decreases as it goes along, doesn't it? The velocity is going to get smaller and smaller, and eventually it's going to reach 0 at its maximum height. So if I call that m, at the point m it's going to be 0 vertical velocity. Then the velocity is going to increase as we come down the other side, and in fact when we reach r, the velocity is going to be exactly the same magnitude as the velocity with which we started, but it's going to be pointing in the opposite direction. So our velocity when we reach the end of the trajectory is going to be minus u. And I'm going to use that for the fact that in my equation of motion. So initial velocity uy is u. The final velocity in the y direction is going to be minus u. The acceleration is going to be downwards. A is going to be in the negative direction, so it's going to be minus 9.8 meters per second squared. And we know the time, okay, because we worked it out from part 1. So t is going to be 40 over u. So with that information, we can now calculate, we can now go on and work out what or we can plug this information into one of the Suvat equations. The Suvat equations we're going to want is going to be one that relates the initial velocity to the final velocity, the acceleration and the time. So it's going to be v equals u plus at. That's the equation we want to use. Or I should say vy, the final velocity in the y direction, is the initial velocity in the y direction plus at. If I now plug in these values, right, the final velocity in the y direction is minus u. The initial velocity is plus u. The acceleration is minus 9.8, and the time taken is 40 over u. Right, so if I bring the minus 9.8 times 40u over this side, so it becomes 9.8 times 40 over u. That becomes bring it over to this side of the equation, and this minus u I'm going to take over to the other side of the equation, and when we add, so it's going to be another u added to the other side, so this is going to be equal to 2u. And when I multiply both sides by u and divide by 2, I end up with u squared equals 9.8 times 40 over 2. And when I take the square root of that, we're going to get that, if I just move this up slightly so that make sure it's on the in view. So we're going to get that u is going to be equal to the square root of 9.8 times 40 over 2, which is going to be equal to 14 meters per second. Okay, so that's part A. Right. Now, for part B, right, so let's now look at one part B. And it says, show that the highest point of the path of the ball is 10 metres above the ground. So I'm going to re-sketch this diagram very quickly. So it goes like this, doesn't it? It's got an initial velocity of 2u in the x direction and initial velocity of u in the y direction. This is the m is the point of maximum height. Start at O. This was R, wasn't it? And this was our horizontal ground. I should have put that in, I suppose. And the thing to remember with this one is, when do we reach the maximum height? Well, we reach if the maximum height is reached at when the time t is going to be half the time it takes to go all of the way from O to R. So t is going to be the value that we've just worked out for part A, or that we used in part A, which was 40. What did we get? Yeah, we got 40 over u. So it's going to be a half of 40 over u is the time to reach maximum height. Max height. Okay, so that's going to be useful to us. So, so looking at the vertical motion, where we once again we're going to choose upwards as our positive direction. And what do we get here? Well, we get that u, going back to our information here, we know that our initial vertical velocity, that's uy, is u. And of course, we've said already it gets smaller and smaller. It eventually reaches 0 in the vertical direction when it reaches m, doesn't it? So Vy, the final velocity of y, is going to be 0 when we reach the maximum height. Oh, by the way, vertical motion between O and m, just to let the examiner know that we're dealing with that part of the trajectory. So we know the acceleration is 9.8 meters per second squared. So, and a is going to be, therefore a is going to be minus 9.8 meters per second squared, because we're acting downwards. And we want the height s. S is going to be the height that we're looking for. So s, the height, is the thing that we're trying to find. So I'll put a little question mark there. And the t, the time, we know is a half of 40 over u, which is 20 over u. So 20 over u seconds. So so using the Suvat equation, s equals ut plus a half at squared, we're going to get s is u times 20 over u, and then we've got a half at squared. Well, a is minus 9.8, we've got a half, so and t is 20 over u, so if we plug that, so it's going to become minus a half times 9.8 times 20 over u squared. Right, so now we know that u, from the first part, we worked out the value of u, it's 14, isn't it? So let's plug that in now. And by the way, I'm going to cancel this u times 20 over u, well, the u's are going to cancel out, aren't they? So s is going to be 20 minus 4.9, because 9.8 divided by 2 is 4.9, so it's 4.9 times 20 over 14 squared. Okay, and when you work that out, I think you'll find that's equal to 10 meters. Okay, so there's our maximum height. Right, C, it says find in meters per second to two significant figures the speed of the ball 2.5 seconds after the ball has been hit. Let's do, I'm using a scrappy bit of paper, I know, but it's, I should have got some more paper anyway. I'm doing one part C over here, one part C, and we find, so this time 2.5 seconds after the ball has been hit. Now it's interesting to see, to ask yourself, whereabouts would that be on the trajectory? When we started at O, there's the maximum height, there's the final position, and we are, and we know that the time it took to go from O to R is 40 over U, and 40 over U is 40, if you think of the time to get here is 40 over U, and which is 40 over 14, and which is, I should have worked this out, I think I've got it down, yeah, 40 over 14, which 40 divided by 40, I'm just, is 20 over 7, which is 2.9 seconds. So 2.9 seconds is here at the end of the range. So half of 2.9 is 1.45, isn't it? So we know that the time it took to get to the middle of the or to its maximum height is 1.45, or roughly 1.5 to two significant figures. So when they say in this question, find in meters per second the speed when the ball, after the ball has been flying in flight for 2.5 seconds, it's going to be between M and R, isn't it? 1.5 and 2.9. So it's going to be over here somewhere. So T is 2.5 is going to be around here. So now our components of velocity at this point, we're going to be the speed. We're going to be travelling downwards in this direction, and we're going to have two components of velocity: a horizontal component and a vertical component. Right. Now the horizontal component is the same as it started. The horizontal component of which we had at the very beginning was 2u, wasn't it? And we know u is 14, so we know if we plug in, we know that the horizontal component of velocity remains unchanged. So its starting value, its initial value equals 2u, which is 2 times 14, which is 28 meters per second. So we know that this component of velocity here is 28 meters per second. But we need to work out what the vertical component of velocity is. Okay, so we need to know the velocity here, v in the y direction, the final velocity in the y direction, and if I call this point P, and I now consider the motion of the vertical motion at a time between when the particle is at M, the golf ball, I keep saying, particle is at M and the golf ball is at P, that so if we consider vertical motion, this time I'm going to taking downwards equal to positive between M and P. I'm going to now consider that, but consider the vertical motion taking downwards as positive. Now you might wonder why I've suddenly changed from upwards to positive to downwards to positive. There's a good reason for that. But we're only considering the motion between M and P. Now, during the motion between m and p, gravity is acting downwards, isn't it? So therefore the acceleration is 9.81, or 9.8, sorry, meters per second squared, acting downwards. Okay, our initial velocity, remember that when we reach the maximum height, so our velocity started off as u, then it got smaller and smaller as it got closer and closer to the maximum. So at the maximum position, the vertical velocity is 0. So the initial velocity vertically at m, in the considering only the y, only direction in the y direction, uy is equal to 0. Right. We're trying to find Vy, so this is, we want the final velocity after the time it's taken to move from M to P. Well, the time it's taken, so this is the thing we're trying to find. Now, the time it takes to move from M to P is not 2.5 seconds. It's the difference between 2.5 and 1.5, because that's the time difference between M and P. So T in our equation is going to be not 2.5 but 2.5 minus 1.5, which is 1 second, isn't it? And finally, we're going to and our acceleration A, because we've now chosen downwards as positive, the acceleration is just going to be 9.8 meters per second squared. So what Suvat equation do we use if we've got u, v, a and t? And you'll remember that this is v, we need v equals u plus at in order to work out what v is. So or I should say, when we're considering as we're considering vertical motion, this is Vy equals Uy plus At. Right, well, Vy is the thing we're trying to find, so we don't know that yet. But we know that Uy is 0, so we can put that in 0. Acceleration is 9.8, and the time is 1 second. So, nice and conveniently, Vy turns out to be 9.8 meters per second. Right. Now the question wanted the speed of the ball after 2.5 seconds. So we need to combine these two velocities. These are just the components of the velocities, horizontally and vertically. Okay. So we need to combine these together to get our actual velocity at that point, or the magnitude of that velocity at that point. So you'll recall, that so if we're trying to find, if we've got a vector, we want to find the magnitude of this vector given its two components. We now know that the vertical component is 9.8 and the horizontal component is 28. So combining these two velocities to find v, this velocity v is going to be the square root of 9.8 squared plus 28 squared. And I think I worked this out earlier, so I'll just check. Yeah. Yeah. Well, when you work that out, you get an answer which is, I think it's roughly 30 meters per second. Okay, and that's the magnitude, or I should say the magnet. Sometimes you need to put two bars there to tell us that we're talking about the magnitude of the velocity at that point. Okay, so that's 1 part C. Now 1 part D, we don't need to really write much about this. What assumptions have we made? Well, I think one obvious one is that we've neglected air resistance, haven't we? So we've neglected air resistance, which is one of the reasons why, in fact, if you look at a golf ball and you see all those little dimples in a golf ball, one of the reasons they have those dimples is to help overcome air resistance. So clearly, in a real situation with a golf ball, you would need to consider air resistance. And the golf ball, yeah. So that's one of our assumptions. Another one is that we're treating the golf ball as a point particle. Okay, so we're not treating it like we're not considering the fact that it might not be round and it might have a different shape. So we're we're modelling the ball as a point particle. So we're not worried about whether it's sort of oval or round, perfectly round or anything like that. And I mean, there are other assumptions. I mean, we assume that after the ball has been hit, that it hasn't been. I mean, I don't know if you've ever looked at a golf ball, but sometimes you find that there's a slice missing out of a golf ball where the golf club has actually removed part of the golf ball when it hit the ball. So another assumption that we've made is that the mass of the ball remains constant during the motion. And I mean, you can go on and think of other things. Another thing is that gravity, obviously when you go above the ground, the value of gravity gets less because you're further away from the centre of the earth. So we've assumed that gravity is constant, which is probably a better one, is a constant. Because obviously that's when you go above, when you go to the top of a mountain and measure the acceleration due to gravity, it's less than it is when you're at the base of the mountain. So now over that distance, I mean, we've only gone 10 metres above the ground, so that's going to make a negligible amount of effect. But we've made that assumption in our question. Okay, well, I hope that's helped with this question, and I'll leave it at that.